So we're going to introduce this notion of Snoopy cache coherence, or Snoopy cache. And this is work by Jim Goodman and one of his students, who's now, I think, a UC Irvine faculty member. And they had this idea that have the cache watch, or what they'll call as snoop, either DMA transfers, or later it was extended to transactions from other processors, other caches. And then do the right thing. Now, what do we mean by do the right thing? Well, I'm purposely being a little bit vague there, because there's sort of two classes of ideas that you can do for doing the right thing. But the most basic do the right thing is if a cache sees a memory transaction go by for an address it has inside the cache, it needs to take some action. Now, what is that action could be? Well, maybe the most basic thing it could do is if it sees that transaction go by and it knows that it has an address which is going across the bus and someone's trying to do a memory transaction for an address which it's caching, it might need to at least tell the other entity that something is going on, that it has the more up-to-date copy somehow. And we're going to look at, in today's class, two different protocols, or two different classes of protocols to handle this problem. Now, if we go look at this, the implementation of this, we have a processor and we have a cache. And what do we have in a cache? Well, we have the data array, which actually has the data. And then you also have a tag and state array. So the tags have the tag match logic, and it also has the actual tags, the upper bits, if you will, of the address. And the state array has whether the data is dirty and whether it's valid, and usually sort of least recently used or most recently used information. And the insight that the Snoopy cache work had was that instead of having only one port into the tag array, the tag and state array, instead you add a second port. So the second port here is attached to the memory bus. And this second port has to watch all transactions on the bus. And if it sees a transaction which has an address that is, it has in its cache already, it has to somehow signal that there's a case where there's going to be stale data and something needs to be done. So that might include removing the data from its own cache. That might include it sending the data across the bus and telling the other entity, the other processor will say, or DMA engine that's trying to read the data to wait a little bit. And we're going to look at that over the next few slides of what different things can be done there. But what's the downside to something like this snooping protocol? Well, every entity, every processor, or every cache that sits on the shared bus has to watch all memory transactions. So they have to watch everything. And the problem with this is the processor here wants to be able to access this cache. So it wants to be able to do operations concurrently while there's stuff happening on the bus which is not related to it. So this requires our Snoopy cache tags to be dual port. So there's two ports to these tags, which makes this bigger and potentially waste power, et cetera. OK, so let's take a look at our shared memory multiprocessor now that we are thinking about having snooping caches, or Snoopy caches. So in this picture here, we now have a shared memory bus in the middle. We have three processors on the left. And we have three Snoopy caches. So now, whenever, let's say, processor 3 tries to do a transaction, it needs to, let's say, broadcast onto the bus that it's trying to read a certain address. The other caches need to be notified of that, and they need to check their own tags and then do the right thing. So what does do the right thing mean? So let's take a look at that. And we're going to broadly put Snoopy cache coherence protocols into two different categories here. The first one we're going to call is update protocols, and the second one is going to be invalidation protocols. So what's the difference? Well, we're trying to maintain the data to be consistent amongst all of the caches. So we're trying to get rid of the stale data. The first thing we can do is we can try to do a write update, or what sometimes people will call broadcast-based protocols. So the basic idea is whenever you do a write to your cache, you also write that onto the bus, and everyone is listening on the bus, everyone's snooping on the bus. And if you, let's say processor 1 does a write to address 5. If processor 2 has address 5 in its cache, it's going to see the write, and it's going to take the updated data and update itself. So this is going to, this is sort of the moral equivalent of the write-through case we saw before, but now on the bus, when someone does a write, everyone updates their local caches by listening on the bus for the particular address and listening for the new updated data. So it's a broadcast. So every write you do that transitions, or every write you do sort of through a memory transaction is going to update all of the other caches in the system. Now, why is this good? Well, it guarantees that when another processor tries to do a read of, let's say, that address 5, it no longer has a stale value. It has now the most up-to-date value because we broadcasted it and we updated in place. And we'll talk about that in a little more detail in a second. Second thing you can do is what is actually more commonplace today is called an invalidation protocol, or a write invalidate protocol. And in a write invalidate protocol, whenever you do a write, you invalidate all other copies of a piece of data. And by invalidating all other copies, you've effectively, or all other cache copies, you've effectively removed the possibility that you could have stale data. So let's look at these two protocols in more detail here. So first of all, we'll look at a write update based protocol, or a broadcast based protocol. And we're going to look at two cases, a write miss to the cache and a read miss to the cache. OK, first of all, a write miss. So you go to a write miss. Well, if you miss in your cache and you're doing a write, you tell everyone else in the system that you are doing the write, and all other processors which are listening to the bus update their copies in place. So you broadcast on the bus, I'm running to address 5. Someone else has address 5 in their cache. They update their copy internally. OK, that sounds not so bad, but that's a lot of bandwidth there. You're basically broadcasting writes to everybody. Let's look at the read side. On the read miss case here, you know that main memory is always up to date because you are forced to basically write through to main memory. So you just go to main memory on a read miss. And you don't have to even sort of check other caches. Let's look at a read hit. A read hit in your cache, you know that the data is in your cache, and you know the data is up to date. So you don't have to worry. OK, so that's a update protocol. Let's take a look at a write invalidate protocol. What happens on a write miss and a read miss. So on a write miss in a invalidation-based protocol, you're going to actually invalidate all of the other caches which have that address in them before you are allowed to do the write. Now, how does this work? Well, on that shared multi-drop bus, you scream, I'm going to do a write to address 5. And everyone else, because they have a Snoopy cache, is listening. And they hear, someone is doing a write to address 5. And what they do is they invalidate their data. They remove it from their cache. And by virtue of them removing it from their cache, you can no longer have a stale value in their cache. Now, I will want to point out here, though, that one of the things you might have to do is when you go to do the invalidate, you might actually have to write back that data to main memory somehow. Because if you have let's say, a write back cache and a different processor has a dirty piece of data, let's say for address 5, and then processor 1 tries to write that data, well, at some point you need to sort of merge the data in a cache line. Processor 2 might have to go and invalidate. But at least it knows that it has to do this invalidation. And it has to do that invalidation before processor 1 does the write. But we can do this all on our Snoopy shared bus. OK, what happens on a read miss? Well, if no one else has the copy, this is easy. You scream on the bus, you scream in the room saying, does anyone have address 5? And then if it's an empty room, no one yells back. And no other caches have that data. But conversely, if someone has a dirty copy of that data, they need to write it back to main memory, and you need to read that most up-to-date copy. So they need to flush the data and potentially invalidate the data depending on the cache coherence protocol. And we're going to look at a couple different cases of that. So before I move off this, I also wanted to sort of point out when write invalidate protocols versus write update or broadcast protocols are good and vice versa. So most processors you'll see today use some sort of invalidation protocol. And generally, those actually are going to work better because there's going to be less bandwidth across your bus, because you only need to communicate across the bus when you take a cache miss for a write or a read. Conversely, update protocols, you basically have to broadcast all your updates. But the cases where an update-based protocol actually wins is if you have many readers and one writer. So let's say you have 5 processors which are reading the output of one processor via memory. So you have some sort of producer-consumer relationship. In an update-based protocol, you can have that one processor just write, and it will broadcast and push the data to the 5 processors that are trying to do the read. In the invalidation protocol, what's going to happen is you're basically going to have invalidates bouncing the data back and forth every time you do a read or a write. So there's actually could be more bus communication in the invalidation protocol for one writer, multi-reader cases. But for the rest of today, we're going to focus on invalidation or write invalidate protocols on a Snoopy bus. OK, so let's take a look at the extra information you need to add into a cache in order to go implement something like a write invalidate protocol. And we're going to look at a base case here, which is called a MSI protocol. This is one of the basic ones that you'll see. And there's some extra bits that are added here. So let's look at the tag information. So we have a tag for your processor, and typically you have a valid bit. We had talked about having valid bits or dirty bits, valid and dirty bits in something like a processor. Something like a cache, excuse me. So each cache line has this information on a per cache line basis. And instead of having, let's say, one valid bit and one dirty bit, we're going to use these 2 bits to encode a state in a state machine. And we're going to add, so we have 2 bits, so we can encode 4 things. We can definitely encode 3 things in 2 bits. So we're going to actually look at a protocol here that we're going to call the MSI protocol for this, that's named for the state names. So we have M, which is modified, S, which is shared, and I, which is invalid. And we're going to say that Invalid is basically whether the data is valid or not. If you're in the invalid state, it is invalid. If you are in any of the other states here, the data is valid in your cache. But now, instead of having just a dirty bit, which tells you whether the data is dirty or not in your cache, instead, we're going to have two other states here, modified and shared. And what we're going to see is by adding these states, we can guarantee some level of cache coherence. And we're going to implement a cache coherence protocol on top of this. And we're going to remove some of the communication across the bus by remembering whether the data is widely shared or whether we have the sole copy. So what are these three states? I is invalid. It's pretty self-explanatory there. The data in your cache is invalid. You're not allowed to read it. If you try to access something that has an invalid bit set in your state bits, you are going to take a cache miss. And then you have to transition to one of these other two states. M is modified. So modified means that the data in the cache has been modified relative to what is in main memory. So this is dirty data. And then we're going to have this other state here called shared, or S for shared. Well, what is shared? Well, S, or shared state here, is going to mean that you have a read-only copy of the data, and someone else may also have a read-only copy of the data. Hence the term shared. So it's shared amongst multiple people. But we're going to say that when you're in the shared state, you're not allowed to do a write. And one of the things I wanted to point out about this is that each cache line in each cache has this state machine there. So different caches have their own copies of this state information. And the state information only relates to that particular cache or that particular processor. And the state diagram we're going to build up here is only in relationship to processor 1. And we'll see that because it's a Snoopy cache, you might be in a state, and then you might see a transaction go across the bus, and you might have to take some action to keep memory coherent. So let's walk through this basic state diagram here. And we'll see that when we're done, we'll actually have the data be coherent when we go to implement something like this. So what's our first arc here? Well, let's say we have a read miss. We are in the invalidate state, and we do a read miss. And this arc here is basically from invalid, or it is from invalid. I just didn't draw it looping around because otherwise the diagram gets too complex. So you do a read miss. You shout out onto the bus, I want to read some address. Or processor 1 here shouts onto the bus and says, I want to read an address. OK, so something happens on the bus. The other processors might have to do transitions. But ultimately, you're going to get the data or get the cache line from main memory. And you're going to bring it into the shared state. So you now have a read-only copy. You can read this from your cache as much as you want. And you don't have to communicate on the bus anymore then, because you have to just do a cache hit. Now, if you have to do a write, though, things get a little bit more complex. So this is, let's take a look at the case here that you have the data in shared state, but some other processor tries to do a read. So they shout onto the bus, I want to do a read of the address that is in the shared state. Well, if we go look at the state diagram here, that's OK. It's shared. We can have a read-only copy, and someone else can also have a read-only copy at the same time. So we just transition from S to S. We stay in the S state. We don't have to do anything when someone else reads, some other processor reads the data. Now, let's say we're in the shared state, and some other processor yells out onto the bus saying, I have an intent to do a write. I want to do a write to an address that you have in your cache in the shared state, or processor 1 has in the cache in the shared state? Well, we said that stale data causes the incoherence of the data, and that's what we were trying to prevent. So if you see some other processor trying to do a write, you just drop the data from your cache. Now, because you only have a read-only copy, you don't have to write this back. You don't even have to tell anybody about this. You just have to guarantee when they say, I want to do a write, that you transition from S to I. Now, what this means, though, is if processor 1 wants to go read that data in the future, it's going to have to get a copy of it again, because the copy it had is now invalid. OK, let's say you have the data in the shared state, but now you want to do a write to that data. Can you do a write to it while it's in the shared state? No. Why? Because someone else may have a copy of it. You're in the shared state, that means it's shared, and someone else could have a stale copy of that data. So you go to do a write. What you have to do before you transition your state is you need to broadcast your intent to write to that line, or processor 1 has to broadcast onto the Snoopy bus that it wants to write to that line. OK, so it says, I want to do a write, I want to do a write. And before it transitions, it needs to wait or give all the other processors time to invalidate and potentially write back the data. And different processors implement this in different ways. Some processors just wait a certain amount of time. There's a waiting period. So you broadcast saying, I have an intent to write, but I'm not going to do the write until some period of time in the future. It's like a waiting period. That gives enough time for the other processors to snoop the transaction, invalidate the data, and write it back to main memory if they have a copy. Or let's say everyone else only has read-only copies of the data. They need to transition from S to I. So I wanted to point out here that all the different caches in the system don't have to have the data in the same state at the same time. This is a per cache state. So when you have an intent to write, you broadcast this information, and everyone else has to invalidate it from their cache. So whether they have it in S or I, they need to somehow or S or M, they need to transition to I. And only then can you transition to M and actually do the write. Now, I said there's other ways that you can go about doing this besides having a waiting period. One potential thing that people do is they'll actually broadcast their intent to write, but instead of actually doing the write, instead of having a waiting period, they wait for an acknowledgement from all the other caches somehow. It's functionally the same. You can either wait and sort of have a proof knowing that you've waited long enough, or you can wait until everyone has responded back saying, yep, I'm done. OK, so what's this modified state? What does this give you? Well, if you're in the modified state, you can write the data and you can read the data. So let's say processor 1 does a read or a write. Well, you just stay in the modified state, and you can do as many reads and writes as you want, and you never have to communicate on the bus. You have the sole copy. You have the token, if you will. You can read it, you can write it. You're guaranteed that no one else has a copy. OK, so let's say you're in the M state, and some other processor broadcasts their intent to write. You're in the modified state. You have dirty data. You've done a write to this data. Main memory is out of date. So the most basic thing you can do is invalidate your copy and give that copy back to main memory, or write back that data to main memory. And then the other processor will go and read that data from main memory and pull it in their modified state. So you will transition from M to I, and they will transition, let's say, from I to M. OK. One more arc in this diagram here. What happens if you're in the modified state and some other processor tries to do a read or broadcasts an intent to read across the bus? Well, what's nice here is you don't actually have to transition to the invalidation state. And the reason is you have the most up-to-date copy of the data. They need to see the most up-to-date copy of the data so that they don't get any stale data, and you don't have any stale data. But you don't have to transition down to the invalidation state. You potentially could try to go down to this state, but it's going to require you to actually go pull the data back in if you want to do a read in the future. So instead, in the MSI protocol, if another processor tries to do a read, you do the write back first. After you've done the write back, you transition to the shared state. And they pull it in a read-only copy, and you have a read-only copy. So you both will transition to the shared state, or the S state here. OK, so let's look at this in a little bit more detail here. Yeah, sorry, there's one more arc that I missed. Write miss. So if you're in the modified state, or sorry, you're in the invalid state, and you want to do a write to a line. We didn't draw this arc, but there's an arc that goes from invalid all the way around to here. And on this write miss, you broadcast your intent to write. You have to wait for everyone to do their invalidations out to main memory. And in the base case, you pull that data in from main memory, and you enter into the modified state. OK, so let's take a look at a basic two-processor example here, walking through a set of reads and a set of writes, and watch everything that happens here. So we're going to have processor 1 on the top, processor 2 in the bottom, and we're going to walk through different arcs here as processor 1 does reads, and processor 2 does reads, and processor 1 does writes, and processor 2 does writes. So let's say the first thing that happens is processor 1 does a read. And this is all to the same address, or all to the same cache line, or all addresses within a cache line. So processor 1 does a read. We're going to assume that all of the data starts out invalid in all the caches. So usually when you reset your computer system, everyone's caches are invalid. How could they not be? So you're going to do a read miss. It's going to go out to main memory, and you're going to bring the data in to the shared state in processor 1. Processor 2 is going to leave this data invalid for right now. OK, now processor 1 does a write. Well, it broadcasts its intent to write. Processor 2 doesn't have this data, and no one else in the system has the data. So no one screams back, I have the data on the bus. Please wait. So instead, processor 1 just goes ahead and transitions into the modified state. And in this case here, it even has the most up-to-date data. So it won't even have to go out to main memory, potentially. OK, then processor 1 does, let's say, processor 1 can do reads and writes past this point. Now, processor 2 does a read. Well, if processor 2 does a read, now we're going to have two different state transitions happening. We're going to see processor 1 do a state transition and processor 2 do a state transition. So processor 2 is in the invalid state right now. It's going to transition to the shared state on the read miss. At the same time, because processor 1 has it in the modified state, it's going to have to write back the data and transition to the shared state. So both of these processors are now in the shared state. So they both have read-only copies, and the most up-to-date copy has been up-to-date copy of the data has been pushed out to main memory, or written back to main memory. OK, so now let's say processor 2 does a write. It has it in the shared state. This has it in the shared state. Well, when you go to do this write, we're going to see an intent to write coming out of processor 2. And this is actually going to cause processor 1 here to transition from shared to invalid. So this is kind of odd here. Processor 2 is doing something, but it's causing processor 1's state machine to transition. And it's because they're on this shared bus that processor 2 shouts, I'm going to do a write soon. Processor 1 sees this, and it transitions. Once you know that processor 1 has finished this transition, processor 2 now can transition to the modified state and actually continue to do reads or writes to that line. OK, so let's say processor 1 wants to do a read to this line. This line's getting a lot of traffic to it. Processor 2 just wrote it, and it's in the modified state. Processor 1's in the invalid state. All of a sudden, what's going to happen is it's going to want to try to transition to the shared state, but this modified state is going to cause a problem. So we're going to have to wait for the write back to occur here from modified to shared. So it's going to invalidate that data. And then finally, processor 1 is going to be able to bring it into the shared state. OK, so let's say processor 1 now does a read. So it's in the shared state. This is in the shared state. We see the intent to write coming out of processor 1. So processor 2 is going to transition from shared to invalid. And only then are you allowed to transition from shared to modified. And then as we get close to the end here, let's say that processor 2 tries to do a write to round everything out here. So we have processor 1 in the modified state. Processor 2 is in invalid. And it's going to try to go this way, or the arc will probably come like this. At the same time, processor 1 is going to have to invalidate this data somehow. So we see the write try to happen. And what's going to happen is when it sees the intent to write, processor 1 is going to have to transition from modified to invalidate and write back that data. And only then can the write miss occur and processor 2 bring it into the write state, or the modified state, excuse me. And finally, processor 1 can try to do a write. Now, why are we doing this? Well, it's to get this last arc in here, because we want to transition over all the arcs in this diagram. So processor 1 tries to do a write to this address. It has it in invalid. Processor 2 has it in modified. And you'll see that it will broadcast its intent to write. And while it's doing this broadcast, it needs to move from modified to invalidate, write back the data. And then processor 1 brings in the background data and can do a write to that line. OK, so a little bit of an observation here. So we've gone through the basic MSI protocol. But one of the big ideas here is that if a line is in the modified state in one cache, there can only be one copy of that data. And this is the important invariant that allows the MSI Snoopy-based invalidation protocol to work. So this allows the memory to stay coherent because there's only one copy of writable data anywhere. And if you sort of work through this, and I recommend you do work through this, case a little bit more carefully, you'll see that you might have multiple people in the shared state or multiple processors caches that can share data, but those are only read-only copies. So they can read it, they can read it, they can read it. But when someone tries to do a write, you invalidate all of the sharers first. Then you can do the write. And if someone else tries to go read the data, you need to transition from modified to shared. Now, why do we do that? Why can't we leave someone in modified and someone else in shared? Well, it's because by virtue of being in the modified state, that processor can continue to do further writes. So if you continue to do further writes, the cache which brought it in, let's say, the shared state, the read state, wouldn't be able to see those updates. So we guarantee, and the invariant for this whole system is that if a line is in the modified state, then no other cache has a copy of the data, or no other entity in the system has a copy of the data. That's really important. OK, so let's try to enhance this MSI protocol. Why do we want to enhance the MSI protocol? Well, as you might imagine, the MSI protocol actually, you have to communicate across the bus relatively often. And we're going to look at a couple different schemes that reduce the communication traffic across the bus. So you could either have a bus that clocks at a slower speed, or you could have more processors on this bus as you think about better ways to actually implement invalidation-based protocols. And the first one we're going to look at is called MESI. And sometimes people call this the Illinois protocol because this comes from University of Illinois and Janak Patel, his research group. And this dates back to 1984, and there's actually 4 states. So instead of having 3 states, as we saw in the MSI protocol, the insight here was if we're using 2 state bits to implement 3 states, well, we have a 4th state we could use. 2 to the 2 is 4. So we could do 4 states instead of 3 states for the same number of bits. Now the question is, what states do you want to add? Just because you have 4 states doesn't mean your protocol is going to be better. Well, we're going to have an invalid state, a shared state. OK, those look similar as what we had before. And now we're going to have a new state called the exclusive state, or exclusive but unmodified. And this is very similar to the modified and exclusive state, or the M state. And in fact, the insight here is we're going to take the state diagram from MSI and take the modified state and split it into 2 states, M and E, or modified and exclusive. Now, why do we want to do this? Well, what we're going to see is that we're going to be able to reduce the communication on the bus in the case where a processor reads a piece of data and no one else reads or writes that data, and then that same processor later goes to write that data. So if you look at MSI, when you go to do a read, you always brought it into the shared state. In MESI, or MESI protocol, when you go to do a read but no one else has a copy, you're going to bring it into the exclusive state. And this allows you to, you're not allowed to do a write when it's in the exclusive state, but you can upgrade from exclusive to modified without having to communicate across the bus. And this is an important difference than in the MSI protocol, because here in the MSI protocol, if you had something in the shared state and you want to go do a write to it, you need to broadcast your intent to write. And everyone needs to have a Snoop transaction occur on this. But in the MESI protocol, you don't need that extra work there. You know that you have the exclusive read-only copy of the data. So when you go to do a write, you can just go do the write. And we're going to walk through this state diagram now. And it's going to look pretty similar to the MSI protocol. And all of the arcs in this diagram are in relationship to processor 1. And like I said before, different processors can have the same cache line in different states. OK, so let's take a look at this. Step 1, you have a read miss. And it's a read miss, but note I have a little word next to here. So this is going from invalidate on a read miss. And we're going to see that there's going to be 2 arcs coming out of invalidate on a read miss. One that goes into the shared state, and one that's actually going to go into the exclusive state. Now, what does this mean? Well, on a read miss, processor 1 here is going to shout out onto the bus, I want to do a read. On the bus, if someone responds back saying, I have a read, or I have a shared copy of that data, or I have a copy of that data which is read-only, what's going to happen is you're going to transition to the shared state here, because you don't want to invalidate the other cache's data. And this is actually going to be in contrast to if you try to do a read miss, but no one else has a copy right now. Because if no one else has a copy, we're actually going to transition straight to this exclusive state. But we'll get there in a second. So let's say some other processor tries to do a read, and you have it in the shared state. Well, you just stay in the shared state. But you might need to respond back saying that, yes, you have a copy of that data. This is important so that the other processor knows whether to enter into the shared state or the exclusive state when they go to do a read miss. OK, let's say you're in the shared state and you want to do a write to this piece of data. Well, this looks the similar, exact same thing as what happens in the MSI protocol. You try to do the write. You have to broadcast your intent to write. You have to give everyone a chance to either respond to say that they have a copy, and they have to invalidate their copies and write it back to main memory. And then after that, you transition to the modified state, and now you can do your write. And just like as before, if you're in the modified state, you can do a read or write to the line, and you stay in the modified state. OK, so finally, now we come to this interesting case that you're going to go do a read miss, but instead of the data being already shared in other caches or already being in somebody else's cache, you do a read miss, you're in invalid, you come into here, but the data is not shared anywhere. So the data is not shared. Well, what does this mean? Well, you do the read miss here, and you can come into the exclusive state. Why is this good? Well, you have the only readable copy in the system. And why this is useful is if you try to do a write, you don't have to go communicate on the bus anymore. So you're in the exclusive state. Let's say processor 1 tries to do a read. That's fine. You stay here. Now, as before, sort of the exclusive state functionally looks very similar to the shared state. You only have a readable copy of this data. If you try to do a write, you need to do something. But this is the big difference here. When you go to do this write, you don't have to tell anybody about it. As far as everyone else is concerned, you had an exclusive copy, and now you have a modified copy. You just transition your state diagram, you transition the state bits here to being in the modified state, and do the write. So you transition and then do the write. Now, why is this good? As I said, you don't have to communicate on the bus to do this transition. Versus if you were in the MSI protocol, where you only have shared, you need to first broadcast your intent to write, which takes bus bandwidth. It also takes time. And then you can do the transition. So this is trying to save us in this one case here. OK, let's fill in the rest of the arcs here. The rest of the arcs look somewhat similar, except when we sort of come out of the exclusive state. And you'll see why. The write miss case from invalid, this looks the same as MSI. You take a write miss here. You're going to broadcast your intent to write, wait for everyone to write back all their data and invalidate, and then you enter into the modified state. Now, here's the little bit more interesting arc here. Let's say processor 1 has the data in the exclusive state. And then some other processor wants to do a read. Well, processor 1 needs to say, I have a copy of that. So the other processor can't enter into the exclusive state when it tries to do a read. Instead, it's going to come in on this arc here with some shared data into the shared state. But at the same time, processor 1 needs to transition from being in the exclusive state to being in the shared state. And why is this? Well, if some other processor has it in the shared state and you were to stay in the exclusive state, you could potentially try to do a write to that data while the other person has a read-only copy of that data, and you'll get the data out of sync and you'll have stale values. So you need to somehow fix that. And how we fix that is when someone else tries to do a write, or excuse me, when someone else tries to do a read to the data, another processor tries to do a read, we transition from exclusive to shared, and the other processor brings the data in as shared into their cache. OK, let's flesh out the rest of the arcs here. This is similar to what we see before here. If you're in the shared state, you see another processor's intent to write go across the bus for the line that you have. You just have to invalidate it. Thankfully, you don't have to write anything back here because you only have a read-only copy. Similar sort of thing here for the exclusive state. You're in the exclusive state, you only have a read-only copy. You know you will have the only copy in the system, though, but if some other processor tries to do a write, you need to do an invalidate. OK, let's see. We got anything else? Yes, we got a few more arcs. Modified. This looks similar to what we saw before. If you're in the modified state, another processor tries to do a read, you transition to the shared state. Now, and you have to write back the data. But what you'll notice here is you can't transition to the exclusive state in this case. And in fact, the only entry point into the exclusive state is this read miss case here, when the data is not shared or in another cache already. So when another processor tries to do a read, you have to write back the data. You transition to the shared state, but this is the same as what we did in the MSI protocol. A couple other things here. Other processor tries to do a write. You'll see their broadcast of their intent to write. If you're in the modified state, you need to clearly do an invalidate because only one cache can have dirty data. And so you see it, you write it back, and you transition to the invalidation state. And that's the sum of this protocol here. Now, what invariants do we have? Well, we said in the MSI protocol that you can only have one cache or one cache line for an address, or one line only in the modified state in one cache at a time for a particular cache line. So is there something similar here? Well, yes, but it's a little bit different because we took the modified state and we split it into two. Similar sort of invariant here, except now we say that only a given cache line can only be in either modified or exclusive in one cache at any given time. And this guarantees that we never have stale data and guarantees that we have a useful cache coherence protocol. OK. Next class, we're going to expand this and talk about a few other cache coherence protocols. One thing we're going to talk about is what they used in the original AMD Opteron processors, where they actually had more states. They added another state here called the own state, and they went from MESI to MOESI. And this own state is a optimization which allows you to do cache-to-cache transfers and effectively track who has the most up-to-date written data versus having to always write everything out to main memory and do memory-based out to main memory transfers. And we'll also talk a little bit about MESIF, which is something that they use in some of the Intel processors, where they will also split the shared state into another state beyond MESI. So let's stop here for today.